In this video, we're going to look at enthalpy stoichiometry. So we're going to look at determining the mass of a substance that will give a particular energy change, or determining the energy released when a certain mass of a substance reacts. So in our first example, we have the following thermochemical equation. 2 hexanes react with 19 oxygens to produce 12 carbon dioxides and 14 waters, plus 8,326 kilojoules of energy. So this is an exothermic reaction. So the question is, how much energy will be released when 10 grams of hexane is burned completely? So our first step is going to be to find the molar enthalpy of reaction. So we're going to start by looking at the reaction we have. So we see that we have 8,326 kilojoules in this reaction as written, and the reaction has 2 moles of hexane. So we can do this by saying that we have negative 8,326 kilojoules per reaction, and that our reaction has 2 moles of hexane. So by doing this multiplication, the reaction will cancel, and we're going to be left with kilojoules per mole. So that's going to give us negative 4,163 kilojoules per mole of hexane. So we have our molar enthalpy in terms of hexane. That's going to bring us to step 2. So step 2 is going to be to determine how many moles of hexane actually react. So we're talking about hexane here. We have a mass. We're going to convert that into moles. So we're going to start with our mass, which is 10 grams, and we're going to divide that by our molar mass, which is 86.20 grams. So 10 divided by 86.2 gives us 0.116 moles. So now we have the number of moles that actually reacted and the amount of energy that's released per mole. So this is going to allow us to move on to step 3. And step 3 is to determine the reaction enthalpy. And we do this by multiplying our molar enthalpy by the number of moles. So we're going to take this negative 4,163 kilojoules per mole of hexane, and we're going to multiply it by the 0.116 moles of hexane that are actually present in our reaction. And so that's going to cancel out the moles of hexane, giving us just kilojoules. And that gives us an enthalpy change of 482.9, so 483 kilojoules. So that's the amount of energy that will be released during this reaction. Our next example, we have the enthalpy change during the neutralization of 2 moles of sodium hydroxide by sulfuric acid is negative 145 kilojoules. How much energy will be released when 50 milliliters of 0.1 molar sodium hydroxide reacts with excess sulfuric acid? So we're going to start here actually just writing our balanced reaction, as we don't have one. So we know that we have 2 moles of NaOH. That's going to react in a 2-to-1 mole ratio with sulfuric acid to produce sodium sulfate and 2 water molecules, as well as 145 kilojoules of energy. So that's our reaction, and we're going to follow the exact same steps we did in the last example. So step 1 is going to be to find the molar enthalpy. So we're going to take that reaction enthalpy we have, that negative 145 kilojoules in the reaction, and we're going to multiply it by the mole ratio within the reaction itself. So we have 2 moles of sodium hydroxide in the reaction as written. That's going to give us an enthalpy change of negative 72.5 kilojoules per mole of sodium hydroxide. So that's step 1. Step 2, we're going to solve for the number of moles that are actually reacting. And so this time, instead of mass, we have concentration and volume. So we're going to start with our concentration, which is 0.100 moles per liter. And we're going to multiply that to cancel out those liters because we want our answer to be in moles. So we're going to cancel out liters by multiplying by the volume, so 0.050 liters. If we look, liters will cancel here, and we'll be left with moles. And that's going to give us 0.0050 moles of sodium hydroxide. So now that we know how many moles are reacting, and we know the enthalpy per mole, we're able to do step 3, which is solving for the reaction enthalpy. So we're going to take our molar enthalpy, which is 72.5 kilojoules per mole of NaOH, multiply it by the number of moles of NaOH that are actually reacting, and that's going to give us our overall enthalpy for this reaction, which is 0.3625, and we get 2 sig digs, so this is going to be in kilojoules, and so that's going to be approximately equal to 0.36 kilojoules. Okay, we're going to look at our final example now. So consider the thermochemical equation for photosynthesis. So we have 6 carbon dioxide molecules, 6 water molecules combining and absorbing 2,802.5 kilojoules of energy to produce 1 glucose molecule and 6 oxygen molecules. So the question is, what mass of oxygen could be produced if 1.00 times 10 to the 6, so 1 million kilojoules of energy were absorbed? So this is going to be a slightly different procedure than last time, but pretty similar. So step 1 is always going to be finding the molar enthalpy. So the enthalpy change per mole of whatever species we care about. In this case, it's going to be oxygen. So we know that we have 2,802.5 kilojoules in the reaction, and that in our reaction we are producing 6 moles of oxygen. So that means that our molar enthalpy for oxygen is going to be 467 kilojoules per mole. Now we don't have enough information for step 2 as normal. So in previous examples, step 2, we've solved for moles using mass or concentration. We're still going to solve for moles. However, we're going to be using energy for it. So we are going to start with the amount of energy that's available to us. So this 1 million kilojoules. So we're going to start by writing this energy term, 1.00 times 10 to the 6 kilojoules. And we're always multiplying by fractions in our unit analysis. So we have kilojoules on the top of the fraction here. So we're going to take this molar enthalpy and put this kilojoules term, this 467, on the bottom of our fraction. So this is going to be 467 kilojoules, and then moles of O2 are going to go on the top. So if we look at our unit analysis, kilojoules will cancel, and we're left with moles of oxygen. And we get a pretty big number here, so I'm not going to round this right now, so I'm going to keep all my sig digs I can. So 2,141 moles of oxygen, and I'm not going to round in my calculator, so I'm going to keep all the numbers and then I'll round at the very end. So step 3 of this problem is going to be to solve for mass. So I have moles of oxygen now, so to solve for mass I just need my molar mass. So 2,141 moles, and the molar mass, because oxygen is diatomic, is 32 grams per mole. So here, moles are going to cancel, and we're going to be left with grams. So 2,141 times 32 gives us 68,522 grams, which we can divide by 1,000 to get into kilograms. And we're going to have 3 sig digs, so 68.5 kilograms of oxygen would be produced with that amount of energy.